Okay, now there's one basic equilibrium in biochemistry. Well, there's a lot of them, but there's one in particular that's very, very important. And it looks something like this. You've seen it before. It involves water and its dissociation into proton and hydroxyl ion, right? And we know there's an associated equilibrium constant with this. Notice that for our purposes, thinking about this equilibrium, I'm going to drop the EQ, right? But that uppercase K is the equilibrium constant for the dissociation of water. Now, you probably remember, or hopefully you remember, that protons don't in general go floating about by themselves like this, right? So technically, this equilibrium really should be written this way, where you have 2 H2O goes to an hydronium ion, H3O plus OH minus, right? So as long as you remember that you don't have, free protons floating about in solution like, a sodium ion or something like that, then it's okay to write down the way I've written it here. Just, make sure you kind of remember that. Okay, so we can take that equilibrium constant as I've written it there, and we can write this out formally in the way we were talking about before, is ratio of reactants and products. In this case, that equilibrium constant would look something like this, where K equals concentration of protons times concentration of hydroxyl ions divided by concentration of water. Now, again, remember, technically, when you're working in these expressions, when you start putting them into those free energy expressions and things like that, you're dealing with the same number, but it's not the unit carrying number of the concentration. Technically, these expressions, you got to remember, are activity expressions. So it would look something like this times the activity of OH minus divided by the activity of water. That's going to become important here in a moment, right? But nonetheless, most people, the vast majority, will still write these expressions out this way because it's more convenient. And there are situations where there's an intuition that retaining the idea of concentration lets you think about things like certain equilibrium constants and binding constants. We'll come back to that in a few lectures. But nonetheless, you got to remember that formally, these ratios should be expressed as activities. Okay, but as long as you keep that basic idea in the back of your mind, you can work with expressions written with concentration notation. Okay, so we can write that expression out or expand it out so that it looks something like this, multiplying through, where the proton concentration times the hydroxyl concentration is simply equal to that equilibrium constant times the concentration of water. Okay, so this expression carries something a little odd about it, which is the concentration of water. Think about that, right? Does the concentration of water in aqueous solution change very much? No, right? Anybody remember what that concentration of water typically is, right? Or what's the value that is known? It's 55 molar, right? It's the standard concentration of water, unless you're in weird conditions where we're not going to generally be operating. Okay, but who wants to work with 55, the number of 55 in their expressions, right? This is where remembering, again, that these expressions formally are activities, right? Because guess what? The activity of water, where the activity of water is defined as equaling 1. It's when the concentration of water equals 55 molar, right? So 55 molar is defined as an activity of 1 for water. Okay, so with that dispensed with, what you can do now is rewrite this expression so that H plus times OH equals K. And in this case, taking into account the activity coefficient of water, right? Or its the activity of water and its standard state of 55 molar equals 1, this gets another symbol, K sub W, and it's known as the ion product of water, right? So turns out that the ion product of water, or the product of the proton concentration to the hydroxyl concentration, is equal to 1 times 10 to the minus 14, right? Now, if you're retaining, thinking about these as concentrations, you of course would now have to factor in a molar squared term here. But if you remember that these are technically, formally activities, then you don't have to worry about that squared concentration number. And what that also means is that the equivalence point here for the ion product of water, that equilibrium, the concentration of protons equals the concentration of hydroxyls, which equals 1 times 10 to the minus 7th, right? Or the value would equal 1 times 10 to the minus 7th. Okay. Right now, if we're going to step back across that boundary, where we're going to think about this as concentration, because the number is exactly the same, what that would mean is in pure water at 25 degrees, the concentration of proton and hydroxyl surrounded by 55 molar water is equivalent to about 0.1 micromolar, right? Okay. Now, many of the reactions that we're going to consider, we're going to think about, and that we care about, involve changes in proton and hydroxyl ion concentration, essentially, which leads us to now have to think about things like acids and bases, right? Okay, and specifically when we're talking about acids, we're talking about Bronsted acids, right? Not as distinct from Lewis acids, right? Okay, so you guys will remember there's a distinction, right? Say starting with something like a strong acid, for example, hydrochloric acid, whose equilibrium, dissociation equilibrium in aqueous solution is so far in this direction, so far in the direction of ionization, it's essentially complete until the concentration gets ridiculously high, right? So strong acids in aqueous solution their dissociation is so complete that you can think about the concentration of protons as being equivalent to the concentration of the acid that was placed in solution. And the same is also true for strong bases, right? Where a strong base, for example, would be something like sodium hydroxide, again, whose ionization is so shifted in aqueous solution in the direction of ionization that you have sodium ions and hydroxyl ions, right? And the concentration of the hydroxyl is equivalent to the amount of sodium hydroxide that was first dissolved in solution. Okay, but acidity of a solution is a really super important topic in all kinds of other domains that don't just involve strong acids and strong bases, right? Which means we have to think about things like weak acids and bases. Where we can't simply assume the dissociation or the ionization is complete, which means we've got to think about equilibrium again. Okay, so if we abstract this a bit to a weak acid, where H is a proton and A is my acid, right? Which has an associated ionization equilibrium to release a proton and the conjugate base. We know we have an associated equilibrium constant, and I'm going to give it a K sub A. The thing we would care about in most cases is we have a weak acid, and we're thinking about reactions where protons are given off or taken up. We want to know what's the concentration of the proton. How acidic is that solution, since acidity scales with the proton concentration? All right, well, let's see if we can solve for it. We can rearrange this expression, all right? Or I should say we can write out the expression for the equilibrium constant. It would look something like this, following the same logic we've been using up to this point, which is that Ka would simply equal the proton concentration times conjugate base concentration, our products, divided by the concentration of the conjugate acid. And we can multiply that through to get an expression that looks like this, where the proton concentration times the conjugate base concentration is simply equal to the equilibrium constant times the conjugate acid concentration. Okay. Again, the thing we want to know about is the proton concentration, right? Or how acidic the solution is, which means we can solve for that. Which will give us an expression that looks something like this, where now Ka times the concentration of conjugate acid divided by conjugate base, right? Now that's great. That's convenient, right? Except for one thing. These concentration numbers, as I just pointed out when we looked at the ion product, under these idealized conditions or ideal conditions where we typically want to work, most biochemists and many chemists don't want to work in multimolar concentrations of stuff. So under concentrations where we approach ideal solution conditions, our concentration numbers are things like, I don't know, 5 times 10 to the minus 6, or 2.7 times 10 to the minus 7, right? Those are kind of hard numbers to try and have to get your brain around and calculate with quickly. So it'd be much better if we had a more convenient way to express those concentration values. And in 1909, a guy named Sorensen hit on an idea for a simple transformation that makes this a whole lot easier, right? He said, well, if we use a simple little mathematical trick, right? Which is to think about the idea that if I had 1 micromolar proton concentration, that would be equivalent to 1 times 10 to the minus 6th molar, right? And again, recognizing that formally you can't really do this. What I'm going to do with a real concentration number mathematically, but it's a small step given how we defined activities before. The magnitude of that concentration, if you take the minus log of it, you just get a number, right? Which is just 6, right? Now that's real convenient, because that means minus log of a 1 micromolar concentration would give you a number of 6. Well, if we apply that logic to this expression, we can come something kind of useful. So if we apply this minus log idea to that expression we derived a minute ago, you get something that looks like this: minus log of hydrogen ion concentration equals minus log of Ka minus the log of the concentration of conjugate acid divided by the concentration of conjugate base. Okay, kind of cool. So then minus log of the hydrogen ion concentration has got to simply equal minus log the equilibrium constant. I'm going to play a little trick of logarithms. I'm going to flip that ratio over, right, and give it plus log, right, of the concentration of the conjugate base over the conjugate acid, right? And now I'll do one more little definitional shift. I'm gonna make this look a little bit simpler by saying, well, what if the minus log thing, that's a lot of symbols. What if we just say P, the symbol P, we're gonna replace minus log with the symbol P. If you do that, that equation now turns into something quite simple, which looks like this. pH equals pKa plus log concentration of A minus over the concentration of HA. That, of course, is an equation you guys hopefully know and remember, and it's the famous Henderson-Hasselbalch equation. Where Henderson and Hasselbalch, working off of Sorensen's idea, came up with this really simple transformation of the weak acid, weak base equilibrium expression into something that is an incredibly simple and usable tool, whereby if one knows the equilibrium constant for a particular conjugate acid or conjugate base, and if you know the concentrations of the conjugate acid and base you have in solution, you can calculate then with precision the pH of a solution, right? Which is just a fantastically useful thing. And it has all kinds of practical benefits beyond simply being able to calculate the pH if you know the concentrations of a conjugate acid or base that you happen to have in solution, right? There's another really important one. Notice what happens if you take a conjugate acid or a conjugate base and you titrate it. So we're going to go from, let's see, 2, 4, 6, 8, 10, 12, 14, and from 0 0.5 to 1, where on this axis, we're going to think about the pH. We're going to have the pH, right? The minus log the hydrogen ion concentration. And on this y-axis, we're going to have the x-axis, we're going to have hydroxyl equivalents. That's what we're going to titrate with, right? So the more hydroxyl we add, the more basic the solution we get in principle. And now, look what happens if you imagine taking an ion like ammonia, right? So if you take ammonium ion, NH4 plus, right? And if you take that at, at pure concentration of it in solution, protonated, right? And you begin titrating it with hydroxyl ions, the pH of the solution will do something kind of like this. It'll go up, 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 and then it'll flatten, and then it'll rise again, where at a full equivalent of hydroxyl ions, you have fully dissociated ammonia, all right? Or what happens if we take something like formic acid? Again, fully protonated, right, in solution. pH is super low because it's fully protonated, right? You do that, and you start adding in base equivalents. The pH rises, and then hits a point before it then takes off again over here where we have the fully dissociated formate, right? So notice something, really important in both of these cases. What's happening really sort of amazing when you think about it. Right here, in this region, about a half a pH unit or so above and below the equivalence point. That curve stays strikingly flat. So what's happening right at that midpoint in each case, right? Here and here. Well, at that point, in both cases, at the equivalence point, the concentration of the conjugate acid and the conjugate base, right, approximately equal 1. And if you remember the Henderson-Hasselbalch equation, pH equals pK plus log concentration of A minus over the concentration of J. If you take 1 and you take the log of it, what do you get? 0, of course, which means that at the equivalence point, when the concentration of conjugate acid and base equal each other, the pH equals the pK. But more importantly, because the pH is a logarithmic function of that conjugate acid conjugate base ratio, as the concentration approaches that equivalence point on either side, about a half a pH unit or so on either side, the pH doesn't change very much in this region, right? So what that means, of course, is that around the equivalence point, the equilibrium of the conjugate, this weak acid, weak base, will soak up protons or hydroxyl ions into the acid-base equivalent, and the pH doesn't change much. This, of course, is the basis of something that is super important for living cells and biochemists as well, which is the idea of a buffer. Right? Weak acids and weak bases serve as extremely effective pH buffers. And in situations where you have a reaction, and there are lots and lots and lots of them, where the chemistry involved requires the uptake or the release of a proton, so that that reaction will depend very strongly on the ambient pH. By having that reaction running in a buffer solution, you can keep it running for much longer or much more to a much greater extent if the solution is buffered, so that the pH doesn't change and the hydroxyl ion or the proton essentially don't become, or not reactants or not products any longer, right? Okay, so that's a super important idea, this idea of buffers being able to damp out large swings in pH as important chemistry happens in biology. Okay, as I mentioned, buffers are most effective about a half a pH unit or so above and below their pK, right? So if that get too far above the 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 equivalence point, you see, of course, those curves start to take off again, and there's no longer any buffering effect, right? So if you're using a buffer in an experiment, you want to try and be within a half a pH unit or so of the pK of the acid or base you're working with. Okay, so one final point. Since, as I just mentioned, protons, the concentration of protons can have big effects on the equilibrium constant for reactions where a proton is a reactant or a product. And because the free energy is also proportional to the equilibrium constant, the hydrogen ion concentration, or the pH of a solution, can have big effects on the free energies that are measured, right? Okay, so biochemists tend to deal with this by essentially redefining their reference state, right? So instead of just having their standard state, which we talked about last time, or just a little while ago, as being the partial molar free energy of a reactant or a product at 1 molar concentration, they also constrain that standard state to being at pH equivalent to 7. And when you do that, right, the standard state, standard free energy of a reactant or a product under these conditions gets a different symbol, right? And that symbol is still delta G naught, but it gets a prime, where the prime designates standard state of that reactant or product under the normal 1 molar or standard state condition, but also at pH 7, right? Okay, and we'll stop there.